In this video, we're going to talk about Descartes' rule or signs. Suppose you have this polynomial. P of x is negative x cubed, let's make it positive x cubed, minus x squared minus x minus 3. We want to see, and it's in descending order. We want to see how many sign changes there were, starting from the left and going to the right. From positive to negative is a sign change, and then no sign change, and then no sign change. So there is one sign change. So how many possible how many positive real roots can there be? Positive real roots. Now, one's not the friendliest number to start off with. Suppose that there were 7 sign changes. So from 7, there could be 7 positive real roots, or go down by 2. There can be 5 positive real roots, or there can be 3 positive real roots. There can be 1 positive real root. There can be negative 1 positive real roots. There can be negative 3, etc. Or does that make sense? I mean, what would it mean that the number of real roots is negative 3? You can have 5 roots. You can have 1 root. How can you have negative 3 roots? Negative numbers make no sense. So if this number of sign changes, you can have that number or 2 less, or 2 less, or 2 less, until either you get to 0 or 1. If you started with 8 sign changes, an even number, you can have 8 or 6 or 4 or 2. And it makes sense to have no roots, but you can't have negative 2 roots. So you're either going to stop at 1 or 0. In our case, we only have 1 sign change. So there is only 1 positive real root. Because I can't go down 2. You have 1 positive real root. Now, let's look at P of negative x. That is, wherever I see x, I put negative x. Negative x cubed minus x squared minus x. Instead of x, I put negative x minus 3. This is negative x cubed minus x squared plus x minus 3. And it's in descending order. No sign change. Oh, there's a sign change. Oh, another sign change. There are 2 sign changes. Now, for negative x, we're going to find the number of negative real roots. Either there's 2 or 0 negative real roots. Well, let's make up a little table here. You have positive real roots, you have negative real roots, and you have imaginary real roots. Now, the degree of this polynomial is 3. There must be a total of 3 roots. Some may be imaginary, but there's going to be a total number of 3. Now, we know that we can only have 1 positive real root. When it comes to negative, we can have 2 or 0. Since 1 plus 2 is 3, there can't be any imaginary real roots because there needs to be 3 in total. 1 plus 0 is 1. there is one real root. That means 2 must be imaginary. Now, why would this be helpful? If you wanted to find the roots of p of x, you can find a list of the possible rational roots. It's not easy to figure out what the irrational roots are, unless you have a quadratic, and then you can use a quadratic formula. But in the cubic or 4th degree or 5th degree, etc., you're not going to be able to find the imaginary root. You're not going to be able to find their complex roots or their rational roots. But what happens is, if you found one, so this is our list of possible zeros, rational zeros. Let's suppose this is our list of possible rational zeros. And you found out that positive 1 worked. Well, what that tells you is, 1 works, 2/3 won't work. Because if it worked, then there'll be 2 positive real roots. But we know there's only 1. So you don't have to bother trying these. Now, you try -7. And -7 works. -7 worked. That means we're not in this case. We don't have 0 negative real roots. We must have 2. You found 1, now go and find the other. Hopefully, it will not be a negative irrational real root. But I guarantee you there will be another rational 0. And a negative 1 at that. Okay. So this is the power of Descartes' theorem, Descartes' rule or signs. If you know that there's exactly 1 positive real root, and you listed their rationals, and one of them worked, maybe 9/2 worked, okay? 9/2 worked. Okay? What that tells us is that +1 won't work, +2 won't work, +7 won't work. Because there's only 1 positive rational root. Okay, and we found 1. It happened to be rational, but there's only 1 positive real root. And we found it. So we're not going to look at those other 3. Likewise, if we found that -7 worked, then I would definitely hope that -1 or -2/3 or -9/2 would work. But again, if we were already down to a quadratic equation, we can use the quadratic formula to find the other 2. Suppose you have this problem. Suppose that the polynomial p of x is 2x to the 4th, say, plus 15x cubed, I don't know, plus 31x squared, plus 20x, plus 4. And you want to find out, you want to use Descartes' rule to find out the number of positive real roots and the possible numbers of negative real roots. Well, everything here is positive. Positive, the positive, the positive, the positive, the positive. So you have 0 sign changes. You have 0 sign changes, which implies you have 0 positive rational, 0 positive real roots. Now, real roots. This is very, very powerful, because if you did the constant divided by the leading coefficient, the numbers that go into 4 are plus minus 1, plus minus 2, plus minus 4. The numbers that go into 2 are plus minus 1, plus minus 2. The possible rational zeros will be plus minus 1, plus minus a half, plus minus 2, plus minus 4. Okay, I think I got all of them. But now, very, very quick, after very, very quick inspection, I noticed the 0 sign changes. That means I won't bother checking half of them. That's really powerful. If this is an exam, oh, no sign changes. Let's rule out 0 and a half and 2 and 4. Now, let's look at P of negative x. Hopefully, it too has 0. That means all the roots or zeros, it has 0 sign changes. That would mean that all the zeros or roots are imaginary. So you have 2 times x to the 4th plus 15x cubed plus 31x squared plus 20x plus 4. If they plug negative x in, so do we. And we get 2x to the 4th minus 15x cubed plus 31x squared minus 20x plus 4. That's one sign change, a second, a third, and a fourth. So we have 4 sign changes. That means 4, go down 2, go down 2, stop at 0. There are 4, 2, or 0 negative real roots. Okay, so now, if you tested all of them and you found 0, well then you're done. If you tested them and at some point you found 1, go and look for the second one. Now, if you're going to have to find the second one. It may not be rational, but hopefully it is. And then if you found the second one, you have to look for the third one. And if you find the third one, I guarantee you they're the fourth one. So, let us make up the table. Positive real roots, negative real roots, and imaginary real roots. Well, we know there are 0 positive real roots. 0. I'm going to write it 3 times. Because along with the 0 positive real roots, there can be 4 negative real roots. Or with the 0 positive real roots, there can be 2 negative. Or there can also be both positive and negatives can be 0. There can be no real roots. And since our polynomial is to the 4th degree, there will be 4 zeros. Since this already 0 and 4 add up to 4, there won't be any imaginary zeros. Any imaginary roots. Because this row has to add up to 4. So far this row adds up to 2. So imaginary has to be 2. This row adds up to 2. 0. Adds up to 0. So you have to add 4 to make this row add up to 4. So either there are 0 positive real roots, 4 negative real roots, and no imaginary roots. Or there are 0 real positive real roots, 2 negative real roots, and 2 imaginary real roots. Or there are 0 positive real roots, 0 negative real roots, and 4 imaginary real roots. It's one of them. Suppose you have the following. So same question. P of x is negative 3x to the 5th plus 4x to the 4th plus 2x cubed minus 3x squared plus 4x plus 5. Suppose you have this. There's a sign change, no sign change, positive to negative is a sign change, negative positive is a sign change, and then no sign changes. So we have 3 sign changes for P of x. That means there will be 3 or 1 positive real roots. That's from P of x. Now, P of negative x, well, P of x is negative 3x to the 5th plus 4x to the 4th plus 2x cubed minus 3x squared plus 4x plus 5. So P of negative x will be this. This will become 3x to the 5th plus 4x to the 4th minus 2x cubed minus 3x squared minus 4x plus 5. That's an understood plus. No sign change, sign change. Negative to negative, none. Negative to negative, negative to positive. There are 2 sign changes. So there will be 2 or 0 P of negative x. Negative real roots. So now, when we make the table, positive real roots, negative, and imaginary, we fill in the imaginary at the end. When it comes to positive, we have 3 or 1. We can have 3 positive and 2 negatives, or we can have 3 positive and no negatives. That took care of the 3 positive real roots. But we can also have 1 positive real root. 1 positive and 2 negative, or 1 positive and no negative. These are the 4 possibilities, and since the polynomial was of degree 5, these 3 numbers should add up to 5, meaning the third one is 0. These 3 numbers should add up to 5, meaning the last one is 2. 1 plus 2 is 3. We need 2 more to get to 5. And we have 1 more row, sorry. 1 plus 1 is... It's either 2 or 0, excuse me. So 1 plus 0 plus 4 gives me 5. These are the possible answers. Okay. Since it is a 5th degree polynomial, negative 3x to the 5th plus 4x to the 4th plus 2x cubed minus 3x squared plus 4x plus 5. If you find 1 negative root, that means it'll be, say it was 7. So you have x minus negative 7. And then you find another one. It is negative 3. So it becomes x plus 3. The next will be a cubic equation, because this is going to be x squared. And what do you multiply an x squared by? To get x to the 5th and x to the 3. So now, the thing is that when you have a cubic, there's no real formula. So, we know one of two things if you found two negatives. Either we're in this case or this case, not those two. Because those two have 0 negatives, and we found 2 of them. So this is gone, and this is gone. So I guarantee you that there will be at least one positive real root. So go and find it. Go and find it. X plus 7, x plus 3, and you find one. It's 4. It'll be x minus 4. Well, if you factor a cubic by x minus 4, you're gonna get 1 degree less. You're gonna get a quadratic. Now, since we found 1, you can look for a second and third one, because either there's just one positive real root or 3. But once you have a quadratic, you can maybe factor it by inspection, you can factor it by grouping, you could factor it by completing the square, you can use a quadratic formula. Once you get down to quadratic, you can find the last 2 roots. Okay, you can find them. Now, just want to make one comment. If the table turned out to look like this, and you have a 5th degree, the table turned out to look like this. Let's see if I can get what I want. Say you have 3 and 0. Okay? That's all you have. 3 and 0. Okay? 1 and 0. You know it failed because you already found more than 1. You found 3 positive roots. Now, the thing is, do you bother to look? Okay. Let's suppose it was this. 3, 1, and 1, 1. Okay? 3, 1, and 1, 1. Now, one can argue that's not possible, but I want to make a point, so ignore that. You found your 1, and then you found your 2nd, and then you found your 3rd. So this one is out. Okay? Complex roots come in pairs. Okay? They come in pairs. There will have to be 2 of them. They can't be 1. They can't be 1. I mean, these numbers add up to 5, but it can't be. It has to be 3, 0, and 2. Okay. Think about that. Let us suppose we have one more problem. Suppose you have p of x is equal to, 2 minus x to the 5th plus x squared. I would write this in descending order. There is one sign change. Goes from positive to positive is not. Notice, if you didn't put it in order, you have a sign change and then another sign change. You have one sign change. One sign change implies one positive real root. Guaranteed. And why is it a positive real root? Because we're looking at p of x. When we look at p of negative x, that changes. P of negative x, I will use this rule, is x to the fifth plus negative x to the fifth plus x squared plus 2. And you plug in negative x. This will become positive x to the fifth plus x squared plus 2. 0. Sign changes, which implies 0 negative real roots, which is good because there's no two possibilities for positive real roots. Like if we had 3 sign changes, it can be 3 or 1 real root. But here, just one answer. 1. Okay, so that makes life easy when it comes to the table. Positive real roots, negative real roots, and imaginary real roots. Well, we have 1 positive and no negative and 4 imaginaries. Because what do you add to 1 plus 0 to get to 5? The answer is 4, which is a pair. You have 2 pairs. This finishes up this section on Descartes' rule of signs.